Hello, good GD&T people. It's great to have you back for what's now my third episode of this video series, meant to address a big question I have about the GD&T system. And this has to do with datum feature selection, what I think of as the hardest thing about GD&T, and an attitude I have developed about the importance of functional datum features. But before we move on, I want to tell you, man, this episode has been beating me up, okay? It took me weeks. I had to do some rewriting, and then in editing, I noticed some mistakes, and I decided I needed to go and reshoot some clips. So you may notice the clips that were recorded at an earlier or later time. I'm wearing the same sweater here, but it'll be hard to get everything exactly matched. Good grief. All I ask is that you focus on the content, which I really try to get right. This is a long one, and there's a lot to cover. I actually think it's going to be great, a tour de force. But in the interest of time, I'm going to avoid giving a thorough recap of the first two videos here and just restate the big question, which I guess is, if I don't have a locating feature to constrain my part in one or more degrees of freedom, do I really have a functional datum feature? And must I have a datum feature at all? And so for all of these videos so far, we've been talking about some version of the blue part you see here as the base of this subassembly, which then gets installed into a pocket on this detail area of a bigger gray part, where we have a close fit on the long edges of the blue part, but then lots of clearance on both ends, and no special feature that jumps out as one that would locate the blue part as it would slide within this pocket. But for whatever the reason, we're going to say that this is the intent of the design, that it have good repeatability with the locating fit, and then we just kind of position it wherever the screw holes will line up. So in episode 2, I introduced this drawing GD&T 00614 as a way to depict the functional requirements of this part. I have datum A assigned to my 2x coplanar surfaces, and I have this undersized but fairly precise 2-inch width identified as the datum B feature. Hopefully nothing controversial so far. Now, probably a lot of us would expect to see another feature, probably orthogonal to datum features A and B, identified as datum C. Well, we do have a datum C here, but that's actually something different, a datum feature for another interface. And we can see in the position tolerance for these 290 diameter screw clearance holes that the datum reference is A primary, B secondary at MMB, but no tertiary datum reference. But then that same exact datum reference is used up here in the 0 at LMC position tolerance for the 3-inch plus or minus 60 thousandths width. And again, over here on a position tolerance for this oversized 1-inch diameter feature. Without the constraint that a tertiary datum would provide, are all of these features just free to drift in X, I guess, here, left and right, disconnected from and unrelated to each other? Well, as I was concluding in the last video, the answer to that is no. All of these features, the way that they're called out, meet the criteria of simultaneous requirements. And so if we were to imagine a perfect gauge with a datum A simulator and a datum B MMB simulator, then we would have to be able to install the blue part and these 3 gauge elements simultaneously. Next, my idea for inspecting the 3-inch width at LMC would be to have something like these no-go blocks, which I said was either correct or close to correct. LMC is tricky. Functionally, the tolerance is meant to ensure that there's enough material on the ends to have a fairly thick section between the screw holes and the ends of the part. And then at the very end of episode 2, I teased this drawing GD&T 00615, in which I addressed the things that make me uncomfortable about 614. So now we have basic dimensions for the width, now 3.2 inches, and a 2x profile tolerance on those ends. This seems to me to be an even more ironclad declaration of simultaneous requirements. And I'm getting quite a bit more confident that I can fully define this part without a tertiary datum feature here. And if there is no feature that locates the part in that 6th degree of freedom, the translation in X, I wonder if we've lost the last thing on this list, the basis on which to identify a datum feature. And if I can define the part and its requirements without a tertiary datum feature, this first bullet under functional datum features would seem to say that I ought not to use a tertiary datum reference. This drawing treats those left and right ends as loose tolerance features, the kind of features that on a more complex part might just fall under the so-called unless otherwise specified profile tolerance that we see on drawings pretty often these days. My point was that this could be preferable to trying to force one of these ends or the center plane of the 3-inch width into being a tertiary datum feature used to locate the screw clearance holes or the 1-inch diameter feature. Because if it's not done carefully, we could end up imposing false requirements onto the part. And what I plan to show you in this video is how those false requirements can result in good functional parts being rejected in inspection or bad parts getting through inspection. So we will look at several approaches to establishing that tertiary constraint off the 3-inch width, starting with the simple, all the way to the quite elaborate. And we'll see what these callouts really do, how accurately they define our functional requirements. Do they solve problems? Do they create new problems? And by the end of this, we'll see that at least one of these is actually pretty good. But I'm thinking still not great, especially if the geometry were any more complicated than this rectangle. But that's all going to be quite a bit later, towards the end of the episode. So let's get started on this little journey, where we take a look at several ways we might extract a tertiary datum reference from the 3-inch width feature. And we'll see how well they match to the functional requirements. For a lot of people, the obvious thing to do is what I have here on GD&T 00622. We pick one of these ends, make it nice and square, call it the datum C feature, and use it as a tertiary datum reference in the position callouts. Okay, now notice that the 3-inch width of the part is toleranced with the loose plus or minus 60 thousandths, because as part of the premise here, we're thinking of these ends as non-critical, like bulk features. Now, one thing to say here is that this is legible GD&T with a clear interpretation. You see examples like this in the standard, and you see it in lots of GD&T explainers that are out there. And as is so often the case, a great way to make sense of these datum references is to imagine an inspection gauge with datum simulators. So in this one, we have a datum A simulator, which is the flat surface, a datum B simulator, which is the width of the groove, and a datum C simulator, which is a special surface on the left there. And what we're meant to do is like we see on the image on the left. We insert our part into the groove and then slide it over until it makes a single point of contact on the datum C simulator. Okay, well, just for starters, this bugs me a little bit when we have a secondary datum reference B at MMB, and then a lower precedence datum reference that is RMB, or not a feature of size like the datum C feature. The datum B feature is meant to be 2DOF and constrain the part in rotation. But by its very nature as a datum feature of size, it has some clearance in here. Isn't the datum C simulator going to try to take over the job of orienting the part, especially since we put that 4 thousandths perpendicularity on there? But then again, we don't want to make this end our secondary datum feature because it's basically a throwaway, a loose tolerance clearance feature. So when I see this, I'm thinking, really? Is this really a datum feature? Is this really how this part locates in the assembly? I guess it could be, but I'm a little skeptical. And there's another thing here, which is that this 3 inches plus or minus 60 thousandths is a mere size dimension, subject to rule number 1 if you want to think that out, and with no clear origin. This plus or minus tolerance does not really locate the rightmost end in the datum reference frame. It's better thought of as a feature of size width feature, together with the leftmost end. You could do this measurement without the gauge, in other words. So that makes it all the more important to control the perpendicularity of the datum C feature, tighter than we may have otherwise done, because any angular deviation is going to project itself to the other side of the part, and possibly get worse because of the loose plus or minus 60 thousandths. So one of the ends, the datum C feature, has tight 4 thousandths control on its perpendicularity and form. But then the other end has what? Approximately 124 thousandths? Yikes. I hope you're able to follow that. Important points, but maybe not the main point. The main problem with this is that if we look at the graphic on the right, the leftmost hole is located very precisely, actually excessively precisely, to the edge, which is our datum C feature. The holes are located with that same precision to each other. That's great. We need that. But then the rightmost end is not located very well at all, as relates to the hole on the right. And that's just because of the way everything is stacked off of the leftmost end, which we're saying is an important datum feature. And the rightmost end is a throwaway, a loose tolerance clearance feature. But when this part gets handed to me, I don't actually know which end is which, unless I do something like make this one chamfer here a little heavier, so I know it's this end that goes to the datum C simulator. The standard says in 4.8, 7.8, and 2018 that datum features must be discernible. So I think you would have to do something like this on the physical part to identify which is the datum C feature. Imagine a crazy situation, though, where we were unable to install the gauge elements with the part in this orientation. But then if we rotated it around 180 degrees, now the gauge elements can install. That would still be a failed inspection and a scrapped part. This is one kind of inconsistency we are going to see a lot of in this video, okay? Situations in which we can think of part geometries that would meet the functional requirements of the design, but would fail to meet the requirements on the drawing and so fail inspection. Here's another example. This is a version of our part that is way out on the wide end of the 3 inches plus or minus 60 width, but the screw holes and the 1-inch diameter feature are all nicely symmetrical about the center of that width. It's a nice looking part. Unfortunately though, if we look at the cross section, we can't get the gauge elements to insert, and so this part would fail inspection. A very similar thing happens when we are narrow on the 3-inch width, but still quite symmetrical. The gauge won't go together, and we fail inspection. It is interesting though with this one, that if we could pull the part away from the datum C simulator just a little bit, the gauge elements would drop right in, wouldn't they? And so here's what those look like in assembly. Pay special attention to where the washers are in relation to the ends. Let's just say for my purposes, either of these would be fine, because even where it's the most wide or the most narrow, we still have good section thickness because of the symmetry. But the way everything is loaded off that one end, our drawing does not reward symmetry, right? These are both failed parts after all. What does our drawing reward? Well, here's a possible part that is about as narrow as it can be, and the screw holes and the 1-inch diameter feature are well enough located to datum C that it can pass inspection. That seems like good news, except now we have this thin section outboard of the second screw hole, which, if there is a functional requirement for this end, is that there needs to be enough material out there. Yeah, in fact, look at this in assembly. Here, the washer on that hole on the right is starting to peek out over the end of the blue part. But this one passes inspection. Maybe we have a hole to edge minimum distance in mind, or maybe it's enough for what we're doing here that I just say, I don't like this. Because now, not only are we rejecting good parts, now we have a geometry that would meet the drawing requirements and so it would pass inspection, but it's getting to where it would not meet the functional requirements. And maybe we could beat this simply by cutting that plus or minus 60 thousandths tolerance in half, but that's always regrettable when we have to tighten a tolerance. Or I guess we could change the design to make the part wider or the spacing of the holes narrower, if we're able to do that. Maybe there's a reason we're stuck with these dimensions. But this is all crazy talk because of course we can dig a little deeper into GD&T and datum references to come up with a better requirement. We've only tried this one thing so far. Maybe a better way to view the problem is that the 13 thousandths diameter tolerance is good for locating the screw holes to each other and to datum B and the 1-inch diameter feature simultaneously, but there needs to be a looser tolerance locating all of that to the datum C leftmost end. So here on GDTG 00623, I have an approach to this that I've seen a lot, and maybe almost implied by the standard as the solution to the problems we had with the last example on GDTG 00622. Like, would it make it possible for the wide but symmetrical part or the narrow but symmetrical part to pass inspection? And would it actually prevent a part like this from passing, in which there is a too narrow section outboard of the rightmost screw hole? Well, let's see. But first, what are some of the changes with this drawing? Well, this is a little aside from the main point, but addressing one of my little issues with the last drawing, this one uses a target for datum C, which is interesting in how it makes this a more convincing one-DOF datum feature. I don't actually think most people would do this, but maybe they should. And then, addressing another one of my little issues, instead of the plus-minus tolerance on the 3-inch width, we're going with a basic dimension and then a 120 thousandths profile tolerance. That's analogous to the old plus or minus 60 thousandths, except now we're locating the feature in the ABC datum reference frame. I like that. I'm not sure everybody will like that, but the GD&T guy does. Well, we're a little off topic, but seeing those two changes together makes me think we can back off the perpendicularity from 4 thousandths to 10 thousandths, or even more. Great. This is really just so you can see some options. But let's get to the big change here, which is that on the call out for the 290 screw clearance holes, and you'll also see for the 1-inch diameter feature, we now have 2 position tolerances. This is something called multiple single segment positional tolerancing, and you can read about that in 7.5.2, where it gets a thorough explanation and several illustrations. So for both the screw holes and the 1-inch diameter feature, the top position is pretty loose at 60 thousandths diameter and references datums A primary, B secondary at MMB, and C tertiary. But then the bottom position tolerance is smaller. For the 290 diameter holes, we have the 13 thousandths, like what we've been seeing earlier. And they drop that datum C tertiary reference. And this is another case where, this is good GD&T, at least in the sense that there's nothing technically wrong with it, I don't think, and that there's a clear interpretation. And that interpretation is that just for the position callouts, since there are 2 position tolerances, there are 2 inspections. The first inspection for the top frame 60 thousandths diameter tolerance, referencing A, B, and C, would use or imagine a gauge setup something like this. In the view on the left, you see that we insert our part into the datum B simulator groove, so it sits on the datum A simulator surface. Then we slide it over to the datum C simulator, which is like a pin that gives us line contact. All right, so moving over to the right side of this graphic, we have gauge elements that are really similar to what we've been seeing all along, only these are substantially smaller. You see, the sizes of the features haven't changed at all. We're just getting smaller virtual conditions because we are subtracting 60 thousandths now from the MMC sizes. And then the rightmost end, with the profile tolerance, would have to have each of its elements inside of a tolerance zone, which is 2 parallel planes if you can see those. There would have to be another tolerance zone for the perpendicularity, but I don't show that here. So you can see there's quite a bit of clearance around these gauge elements here, with the blue part at nominal geometry anyway. And that clearance just represents the larger position tolerance we use when we're taking datum C into account. One thing I want to point out here is that this seems to be like a sort of backwards approximation of what we're really trying to accomplish. What we want to say is that these outside ends are able to move in and out relative to the other features of the part. But what we are actually saying with this callout is that when we take this tertiary datum into account, the virtual conditions of these features get smaller. Wouldn't it be nice if this datum C simulator could translate left and right? Something like that? But that's not what we're dealing with. So that was the first position inspection that takes datum C into account. And now we have the second position inspection, which does not. Now for this one, we are back up to the larger size gauge elements. And these represent the virtual conditions you would get from subtracting the bottom frame position tolerances from the MMC sizes. So what it's saying here is that when we don't take datum C into account, we have these larger virtual conditions. And as a result, even on the nominal geometry for the blue part, there's not very much clearance here between the gauge elements and the features we're inspecting for position. But I want to say, I like how this gauge will keep all the features nicely centered on the datum B feature. I like how it locates the screw clearance holes to one another. And I like how it locates the 1-inch diameter feature with the screw holes as a simultaneous requirement. This is actually taking me back to the way that I originally wanted to inspect this part. And that would have been more like what you see on the right here, with GD&T Guy 00614, where there is no tertiary datum simulator, just gauge elements to check the virtual condition and hold everything as simultaneous. For the picture on the left of the second inspection of GD&T 00623 we've been talking about, if I could get in and locate those end surfaces with a CMM, I would be pretty happy with that. This whole thing with inspection 1 of 2, with the Datum C simulator and the smaller virtual condition pins, this seems like a lot of extra stuff that I don't really need. All right, and here's another interesting thing in terms of our overall question for this entire video series. Isn't it interesting that we are allowing ourselves here to make a position call out with less than 6 DOF constraint? The assumption that I'm challenging here, I guess, is that we have to have enough datum features to create 6 DOF constraint. Is there a rule I don't know about that you can do a 5 DOF inspection, but only once you've done a 6 DOF inspection? Okay, so that's some of our bigger question stuff. But let's bring it back to this set of callouts and see how it does with some different part geometries. All right, so here is the blue part with its 3-inch width, about as large as it can be, around 3.055. But it is also a quite symmetrical part. Now this is a part that we had to reject before, even though we consider it to be perfectly functional. This is a big reason why we're trying out the multi-segment position tolerance. And it is paying off for us here in the first inspection, you can see on the left. Because even though we are pushing at the limits, we are able to assemble our gauge. And even though the 229 diameter pins and the 942 diameter gauge element here are way over to one side, there's still space and you could install them. Okay, and then on the right, the second inspection, we can see that the wide but symmetrical part would pass this one as well. So this is our multi-segment position tolerance paying off, at least in the sense that we are not having to scrap this perfectly good part. Let's have a look at another graphic where you can see a similar situation when we bring in the narrow but symmetrical version of the geometry. We had to reject this one earlier as well. Now in the first frame inspection on the left, our gauge elements will all still install, even though they're shifted all the way over to the other side. And then in the second frame inspection on the right, this one will also pass. So it seems like this set of callouts on GD&T 00623 will allow the symmetrical parts through. Okay, but what if we introduce a new geometry, where the part is about as narrow as it can be, but the features are shifted over, away from datum C about as far as they can go? Well, for this one, the first frame 60 thousandths diameter position tolerance actually allows them to be quite away from datum C, now that we have these smaller gauge elements for this inspection. So yeah, it will pass the first frame inspection, and it will pass the second frame inspection, even though we now have this extra thin section on the rightmost end there. So it seems like the root of the problem is that we've stacked everything off of one end. And however convenient that is, it does seem artificial to choose one of the ends as being a datum feature, but not the other. And then as a mitigation, the multi-segment position tolerance could allow more good parts to pass, but it also could exacerbate the problem with the thin sections near the screw holes and make it so that we're passing even more bad parts through inspection. So I think that multi-segment position is a good tool for some other purposes, but not the right idea here. So that's going to lead a lot of people to look in the direction of having the tertiary datum be another centerplane, the centerplane of the 3-inch width. Let's see what that looks like coming right up. All right, so here we are now on GD&T 00624, which is going to try to solve some of our earlier problems by making the tertiary datum another centerplane datum using this 3-inch dimension. Now that this is a datum feature, we have to establish perpendicularity. I think you're going to see that once we try to bring in the centerplane of this 3-inch feature of size, it's going to be the material modifiers that really become the most relevant thing, especially here in the material boundary modifiers, when we reference this datum C tertiary. And having this large tolerance of plus or minus 60 thousandths is going to exaggerate the effects. Now, I've been saying that this tolerance reflects a design preference I have, that these ends be loose tolerance clearance features. But having it this loose is going to make a big difference when it comes to the material boundary datum modifiers. So we are going to run through a few scenarios for these material boundary modifiers, starting with circle M, like you see here on GD&T 00624. I start with this one partly because I have, especially in the past, Made a lot of drawings of rectangular parts with this approach to the datum references. And also, probably like many of you, I subscribe to the view that circle M is most likely to be correct when we reference datum features of size, unless there's a good reason to go to a different material modifier, and we'll see if there's a good reason, okay? But one of the many great things about circle M is that the datum simulators are very easy to imagine. And so datum C is simulated by the inside faces of these fixed dark purple blocks, which are perfectly square with everything else, of course, and exactly 3.060 apart, which we know is our maximum material boundary by adding the MMC of 3.060 and the perpendicularity tolerance, 0. And the nominal geometry part looks pretty good in here. One thing that is interesting is that because the size tolerance for the datum B feature is so much tighter than the size tolerance for the datum C feature, it kind of helps justify datum B as being a secondary datum and datum C as being a tertiary datum. But kind of on a similar line to what I was saying before, it is also easy to imagine the 3-inch wide datum C feature being made near its MMC, right? Pushing up against the dark purple edges here. And if we were close to the least material condition on the 2-inch wide datum B feature, so the most clearance possible with the datum B simulator, which feature would be orienting the part in that case? Which is the 1-DOF datum reference and which is the 2-DOF? We can really see that when we put into this gauge the geometry that is about as wide as it can be, but where the other features are quite symmetrical. And this one is a pass, okay, because the gauge elements can all go together. But you can see how as the datum C feature approaches MMC, there is very little room for asymmetry of the features in the middle. Now let's look at what we get when we go narrow but symmetrical. So here we still pass inspection, maybe even easily, but it actually points to a now familiar problem, which is that if we were to go all the way narrow, we would have quite a bit of room in the datum C MMB simulator to shift the 290 holes and the 1-inch diameter feature, resulting in that thin section again. There's really nothing in this gauge that would prevent this from happening. Actually, it's kind of incentivized. As the 3-inch wide datum C feature gets smaller, the positional requirements, at least to the left and the right here, the positional requirements get looser. So if you are the manufacturer of this part, you have a bit of an incentive to aim a little on the small side when you produce this 3-inch datum C feature, which is kind of the way of things when it comes to MMC and MMB. The incentive is to produce features closer to LMC because the tolerances become more forgiving. But remember our assembly and our functional part requirements. There's lots of clearance on either side of the blue part. We don't need to incentivize going small on the 3-inch feature. It might be better if we could incentivize going wider, right? In the interest of preserving these section thicknesses. And that's where we would want to try LMB. But LMB can be a little tricky. So let's get there by way of RMB, regardless of material boundary, which doesn't really incentivize a larger or smaller 3-inch feature, but requires centration of the features. So continuing on, let's take a look at this drawing GD&T 00625, where we have datum C referenced as RMB on the position for the 290 diameter holes, as well as the 1-inch diameter feature. Another thing I changed here is the way I control orientation for the datum C feature. I'm making this an RFS callout. The last drawing, GD&T 00624, had 0 perpendicularity at MMC, which, don't be fooled by the 0, is a loose perpendicularity because it would all be within this large plus or minus 60,000 size limit. This drawing 625 is saying, regardless of feature size, the median plane of this 3-inch feature must be 20 thousandths perpendicular within the datum reference frame A primary, B secondary. So even with the large size limit, this will control the extent to which this shape can be tilted like a parallelogram. Interestingly though, it could still be quite trapezoidal and still actually have perfect median plane perpendicularity. Dang. I'm trying to get more perpendicularity control because of the way now, with datum C referenced at RMB, I am going to be gauging in contact with both ends. This would be a pretty exciting, if not outright fanciful gauge, but fun to think about. Probably it's the case that all of these gauges are fanciful. In a way, it's really too bad how few of them ever seem to get made because they'd be so much fun. But if it were real, these elements of the Datum C simulator would have to be able to move in and out while maintaining excellent squareness to the other Datum simulators. But the spiciest thing here is that they would have to be synchronized or metered somehow so that they move toward and away from the center at the same rate, mirroring each other. Nice. And I just kind of hint at such a mechanism by showing this cover on the bottom. You can speculate on what would have to be inside of here, okay? So we would open up the Datum C simulator, set the part to be inspected down into the Datum B simulator groove into full contact with the Datum A simulator, and then we push together the Datum C simulator until they make contact on both ends, centering the part in the gauge. Pretty cool. And then after that, we insert our other gauge elements. One predictable thing that's happened here is that now our wide but symmetrical part geometry is of course going to pass this inspection. And actually any symmetrical geometry is looking pretty good. By which I mean that the 290 diameter screw clearance holes and the 1-inch diameter feature are on like a mirror plane of Datum C here. The problem comes when we are not super symmetrical. This part is 3.040 wide, but the screw holes and the 1-inch diameter feature are shifted 20 thousandths off center, which should be trivial because we still have plenty of section here. Nevertheless, we have to fail this part because the gauge elements won't pass. And that's a shame because the asymmetry is not going to affect the function of the part. Heck, it's barely even noticeable. But maybe that's what you're trying to control. It could be that it's important to you that the part be more than just visibly symmetric. But the way I'm looking at it, that's not what's important. On a lot of the work I've done, if it's pretty, it's a little suspect, right? So yeah, I don't think this is a very good functional datum reference because it prioritizes that symmetry over what I'll say are the real requirements of the part. And here we go again with my little grievances. Another thing that bothers me about this one has to do with the way the Datum C simulators come together to make contact with these ends and center the part. This is similar to some of the stuff I've been saying all along, only worse. How do we continue to call this a one-DOF tertiary datum feature? And then the Datum B simulator groove, with a few thousandths of clearance, how do we continue to call that a 2-DOF secondary datum feature in this setup? When we close up this Datum C simulator, how does it not take over the orientation of the part, at least within the limit of the Datum B simulator, unless these sides are significantly out of square? Maybe I'm an unusual person and overthinking it, but I would have a hard time getting comfortable with this datum reference, knowing what a conflicted situation I could be creating. So that's just one issue with this. But the bigger issue, I'd say, looking back just a minute, is that this callout really prioritizes the symmetry of the features of this part, which is not the functional requirement in this case. We shouldn't scrap good parts just because they're not super symmetrical about some center plane. Well, we're going to give RMB one more chance in the next example. And listen, I'm only showing you these because I've seen all this stuff out in the world. Where there are designers and engineers who know quite a bit about GD&T, they're smart, they can see all these little pitfalls and contradictions, and they go through all these steps that I'm taking you through now. So it's getting a little painful, okay, but somehow it feels like we've got to do this. I've got to do this, to take all of our tools and options provided in the standard and run them to ground. All right, so here we are with drawing GDTG 00626, where we will try to apply a few bandages to our last attempt to use the 3-inch width as an RMB datum feature. First, the small stuff. I'm changing the way I do the perpendicularity of the 3-inch feature, treating these sides as individual features for this requirement. That will limit the extent to which these ends can be trapezoidal or wedged relative to A primary, B secondary. I like that, and it also gives me some form control I didn't have before within the 10 thousandths perpendicularity limit, which is good because now I'm going with these datum targets to identify datum C. And because we're going to be referencing datum C as RMB, these have to be moving datum targets. So those are just some things to deal with my mini grievances. And it just makes this datum C feature more believable as a 1-DOF tertiary datum reference, right? I also like the idea of the inspector, if this is CMM, only having to pick up these little datum target areas and find the midpoint for datum C. Anyway, it's just options, and maybe not as important as I'm making it sound. But the most important things for us on this drawing are where we go back to the multiple single segment position tolerances for the 290 diameter holes and for the 1-inch diameter feature. If the problem with RMB in the last approach was that it was pushing us to where we were making it a requirement that these features were centered on datum C, this now says, as we know from our last look at multi-segment position, in the top frame when we're considering that tertiary datum C, we have a loose 60 thousandths position tolerance, but then when we don't consider datum C, we have a tighter position tolerance. Okay, and so when we go to the gauges, as we've seen before with the 2-segment position callouts, we have a 2-stage inspection. Now in the first stage, we have a datum C simulator, which is 2 pins that can translate toward and away from the part and make tangent contact with the end surfaces. And of course, they are metered by some special mechanism inside the gauge so that they move in and out together, mirrored about the datum C plane in our datum reference frame. Very important to this inspection, the gauge elements are the small ones, right? Because we subtract 60 thousandths from the MMC sizes of these features. So when we look at the nominal geometry part on the gauge, there's quite a bit of clearance around the gauge elements. And that just reflects the relatively loose 60 thousandths diameter tolerance. All right, but then in the second stage of the inspection, there is no datum C simulator, and I have the larger size gauge elements to account for the smaller 13 thousandths and 10 thousandths tolerance. Now this gauge is looking really familiar from before. This is what I've been saying all along is the simple gauge that would address a lot of what I'm looking for when it comes to the functional requirements of this part, without all the fuss. But more on that later. Let's go back to the first stage of this inspection and see what this looks like when we put in the geometry that caused us a problem with the last example on GD&T 00625. This one is pretty wide, 3.040, and our screw holes and 1-inch diameter feature are shifted from the center by 20 thousandths. All right, so we can see that this geometry is going to pass this inspection as all the gauge elements are able to pass through the part. Great. Now we've already seen this same geometry pass an identical second stage of inspection. So this is also a pass. All of these larger gauge elements will fit through the part now that we are free from the datum C constraint. Let's go back to that step 1 of the inspection again. You know, we can see that the features are shifted and this hole on the right is getting closer to the end of the part. But because the part is so wide, we still have the good thick section we are looking for. But what if instead of being wide with shifted features, we look at a geometry with the 3-inch width just about as narrow as it can be and with that same amount of shift? If I toggle back and forth, maybe you can see that nothing really changes except the datum C simulator pins move toward each other and away from each other. It is still a pass because the tolerances apply regardless of material boundary, right? Only now our section thickness near this hole on the right is getting to be pretty thin. Maybe we are back to passing bad parts that meet the drawing requirements, but that do not meet the functional requirements. And just for the record, it would pass the second step of the inspection too. So far, I think everything we've seen would pass the second inspection. So let's do a quick review of what it would take to fail inspection on this gauge. Well, for one example, if these screw holes were too close together, or in this case, too far apart. This one looks like it would pass the first inspection with the smaller virtual condition pins, and it seems to be just fine in terms of its symmetry about datum C. Another one would be if this 1-inch diameter feature were shifted vis-a-vis the screw clearance holes. Remember, these features are all being held as simultaneous requirements. That 10 thousandths position tolerance on the 1-inch diameter feature is pretty tight. If I were the machinist, I might want to produce it and the screw holes in the same setup. All right, so having another look at the drawing GD&T 00626, maybe this is the best we've done so far with this tertiary datum reference, but still has problems. If we could knock down this upper frame position tolerance down to 20 thousandths or 30 thousandths from the 60 thousandths, it might be even better, but it might take us away from our goals of having really loose tolerances related to the ends of the 3-inch width. And maybe this is to state the obvious, but even if they were totally correct, these are some fairly elaborate callouts for what most people are going to think of as a simple part. I would be a little scared to submit this to a reviewer, most places I've worked. But it is funny, isn't it, that a lot of that complication is to establish datum C and then to reference it in this loose tolerance feature control frame. And then shortly after that, we ditch datum C for these tighter, arguably more important tolerances of 10 thousandths diameter here and then 13 thousandths diameter here. So datum C is looking like a throwaway. It's not that the 3-inch width feature is unimportant. We've seen how it can be a problem if it's small or shifted and results in a thin section. But does that mean that it's a datum feature? A feature that we locate other features to? Okay, we'll draw some more conclusions about that in a few minutes. But first, let's look at what I hope will be the best, most functional tertiary datum reference yet, which is going to be if we use LMB. All right, so this is drawing GD&T 00627, and I'm making a little effort to get back to something simpler. So I got rid of the datum targets, for example. And then on the 3-inch width, I went back to putting a perpendicularity up here, only now I'm calling it 0 at LMC, which I think is right. LMC and LMB are always a little mind-boggling to me, but I think this has got to be right. And it always feels a little strange to have circle Ls and circle Ms in the same feature control frame. I'll have to explore that some more someday. Regardless, now where we see datum C as a datum reference, in the screw clearance holes on the 1-inch diameter feature, it is referenced at LMB. And the appeal to that is, if you remember what I was saying earlier, MMB incentivizes a narrower part, usually for the purpose of fit, and LMB incentivizes a wider part. Really pretty often, LMC and LMB are about preserving section thickness. So in this case, the wider the part gets, the looser is the hole position, but it happens in a one-to-one sort of way in which you preserve this section thickness. And it goes the other way too, where the narrower this part gets, the tighter the hole position requirement becomes. Again, preserving section thickness. One inconvenience for me making this video is that it's pretty difficult to come up with a practical LMB gauge for this part, which I remember learning is notoriously difficult. Specifically, the problem is the datum C simulator. It's hard to depict as a physical object. And so what I've put here are the imaginary planes that represent the least material boundary. And then an example of a passing geometry would be our 3.040 wide version with the screw holes and 1-inch diameter features shifted off center by a little bit. So here you can see, hopefully you can see, all of our gauge elements are installed in here, and still the ends are outside of the boundaries. That is, no area of these surfaces dips inside the boundary. Get it? Let's look at a geometry that would fail this inspection, okay? So this one is the version of our part that is about as narrow as it can be, and with shifted features, producing a thin section on the rightmost end there. So for this one, with all the gauge elements installed, the leftmost end would be outside of the boundary. But even if we push the part all the way to the right, as far as we can on those gauge elements, we can't get the right side end to break out past that boundary. So this has to be a fail. And it's a fail for exactly the right reason. I have too little section thickness outboard of this hole on the right. So LMB is looking pretty good, isn't it? It's allowing us to have a loose tolerance on the 3-inch width and preserve our functional requirement. I feel like this is a good drawing, but you don't see a whole lot of LMB out in the world, do you? Maybe there should be more. Probably there should be more. Is LMB going to be viewed as a little over the top for a part like this? Even for people who understand what it means? I don't know. Let's go back to the inspection gauge. How are we going to know where these planes are? And if the edges are inside of them? It's probably going to require a CMM or something along that line, right? So we install our gauge elements, and then we probe these ends to check that they are outside of the boundaries. Okay, well that just seems a little backward to me. If we do it that way, are these boundaries really effectuating a datum? Which is more like a datum simulator here? The center plane of these boundaries or the gauge elements? But that's just one way of looking at it. If you go full open setup CMM inspection, I speculate you could locate datum C off the ends and then locate the 290 holes in the 1-inch diameter feature, and then do a datum shift calculation. All right, that probably works pretty well. I want to tell you, I got pretty far in writing and even recording this episode, and when I got to this point, I became concerned that maybe this isn't the greatest example for my overall point with the series. And that's just because this GDTG00627 drawing that uses LMB actually does a pretty good job describing the functional requirements as I'm thinking of them. And the more I thought about it, having the datum C could open up some other interesting possibilities like multi-segment position on the 1-inch diameter feature. This would put a looser tolerance on the position of that feature in X, as we've been calling it, or left and right along datum B. That's pretty cool. But getting pretty deep in the weeds here, then you would want to make sure that this outside cylindrical feature is located to the 1-inch diameter feature and not to the ABC datum reference frame. And if you do that, it should probably also be an LMC type of deal, or you could lose control of your wall thickness. Good grief. Hold some of these thoughts for episode 4. So here's what I've had to wrap my head around. This whole thing has been about functional datum features, right? And I have kind of equated that with the locating features, which is usually right. Well, this datum C feature, this 3-inch width feature, just fulfills another functional requirement, right? It's not to locate the part. No, it's to ensure that there's enough material outside of these screw holes. Its function is to be there. That's very circle L. Be there. Preserve material. It's the opposite of how, like, circle M is all about clearance. Circle M is all about getting out of the way. Don't be there. Remove material. Well, if you look at this 3-inch dimension, plus or minus 60, perpendicular 0 at LMC, and then the LMB datum references, this isn't really giving us an outer MMC boundary for this feature. Actually, what it says is that if the feature is made closer to the MMC size, 3.060, it could be effectively shifted 120 thousandths if you believe it. So this is with a part on that LMB gauge that's about as wide as it can be, but almost all of that extra width is protruding out the left side. And if you think about it, that left end could also be pretty wildly out of square within that space beyond the leftmost boundary. Is that really what I want? Let's look at where we are now compared to where we were what seems like several hours back towards the beginning of this episode. If you remember this drawing, GDTG00615, which represents my real preference, which is to simply not specify a tertiary constraint when it comes to the slotted screw clearance holes, the 1-inch diameter feature, and also even the ends that make up the 3.2 width feature. Those ends have a profile tolerance with the same datum references as the other features. Located by basic dimensions, simultaneous requirement, I'd say. And so for this one, what I want out of my gauge is something like this, with the datum B simulator and gauge elements, now some special ones for the slotted holes. Then for the ends, I just have these tolerance zones that represent the profile tolerance. This looks a lot like that LMB gauge from a minute ago, doesn't it? Only now it has an actual outer boundary on both sides. Instead of having to think about how this interacts with a datum simulator, we're just saying that every element of those surfaces must lie within the tolerance zone. Here's another look at it with the blue part and the gauge elements installed. I drew some purple dashed lines over the planes of the tolerance zone, hopefully make them a little bit easier to see. If we were forced to be practical about the gauge, maybe we would have to start saying it's a fixture to be used with a CMM, which is how you would probably have to approach these ends. I was even thinking for a minute that maybe you could somehow mark the datum A simulator with 2 sets of lines representing these tolerance zones, and then you would visually confirm the profile. Maybe. But if we're talking CMM, maybe a much simpler fixture could be reasonable, without the special gauge elements, just the datum A and datum B simulators. There might be a way to build something like that with setup blocks. I was also thinking I could open up this profile tolerance even more on the end features using unequally disposed, which is the circle U. That's going to allow me to keep the same basic dimensions 1.6 and 3.2, but then the tolerance zone is 30 thousandths inside of that and 60 thousandths outside of that. Pretty cool. If I wanted to, I could add a perpendicularity refinement which is also pretty cool. But when I do this, okay, treating these as profile features, I'm saying I need there to be material here, but not too much. Bounds of reason. I like this. This is my real intention for these ends. And you know, like I said, LMB might be just fine for this part, but that's just because of its very simple geometry with square ends that are conducive to the LMB approach. Well, this has been a lot, and we'll see when I edit it down. I'm sure this has been a long video. I'm going to cut it off here. So if you stayed on until now, I really appreciate it. I told you from the beginning that I felt almost compelled to make this because of what I think it shows about non-functional datum features. And good news for those of you who are getting tired of looking at my little blue base parts. I think we just have one more to show you before they're going to go bye-bye. But this one will be great because it's going to be about what happens when, forget tertiary, we don't even apparently have secondary constraint on a part or an interface. I see this all the time, especially on parts like this cover plate that have no discernible locating feature, whether they're simply set on top of a housing or installed into a pocket. I'm going to tell you that the outer profile is not particularly conducive to being a datum feature, in most cases, and neither are the screw clearance holes. That topic goes all the way back to episode 1, and I plan to dig into that some more. All right, and it's not just the cover plates. I've come to see that it really doesn't matter how complex a part is for this stuff to apply. This is the base segment of an assembly I'll show you that I'll call the science experiment. And this is going to sit on a table on these 3 flats and possibly get screwed down. There are not really locating features for where this interfaces to the table, although there is lots of other stuff going on with the part, a lot of which is going to fall under the unless otherwise specified profile tolerance. But that's enough for now. Hopefully we've made it through the more tedious portion of the series, and for the 4th and hopefully final episode, we will be on to the really good material where I can show you how this can apply to the challenging parts I assume most of my viewers are designing at their jobs every day. Until then, this is the GD&T Guy, signing out.